Okay, and we are back. Thank you for your patience. We're going to jump right back in here. So chiral molecules are important. We can identify chiral objects, and we are now today going to just talk about chiral molecules. Your proteins, your DNA, sugars, all of these molecules are chiral. They do not have an internal plane of symmetry, and their mirror images are non-superimposable. So now we're going to use our model kit and build some chiral molecules and work to identify when a molecule is chiral and when it is not. So grab two tetrahedral shapes with me and begin with a red ball on each one. So this red ball could indicate a chlorine or a methyl group, but some type of unique group on each of these tetrahedral carbons. So we are going to build the molecule on the left and then build its mirror image on the right. So on the left, I have a molecule. The plain black prongs are going to represent hydrogens, and then my unique group that is my red ball. And then I'm going to build its mirror image. So imagine you're holding a plane or a mirror right between them, and we want to build it such that the red reflects the red, the back black reflects the back black, and so on. These are mirror images, and we want to look at one, and we're going to decide if it has a plane of symmetry. Looking at one molecule, can you find a plane of symmetry? Can I slice it down? If I sliced it this way, obviously you can see the red ball does not reflect on the other side. But if I slice it down, that red central atom, you can see the prong on the right reflects the prong on the left, and I can cut the red ball in half and the black prong in half. So yes, this molecule, as well as this one, has an internal plane of symmetry. And so we can check that off here. Next question, are the mirror images superimposable? We've built them such that these molecules are the mirror images. Are they superimposable? We go and overlay them. And imagine they can be perfectly overlaid. The central atoms overlaying, the red balls overlaid, hydrogen, hydrogen, and hydrogen. So what do we think? Are they superimposable? And the answer is yes, they can overlap perfectly. All the colored balls and pieces can overlap. Therefore, we can classify this molecule as achiral, which means not chiral, because it has an internal plane of symmetry and we can superimpose its mirror images. So now we're going to go to the next option. Add a blue ball onto each of your molecules and build it in such a way that they are mirror images of one another. So the red reflects the red, the blue reflects the blue, and the two black prongs reflect those as well. So imagine you hold this up with your mirror and you can see they perfectly reflect one another. Once we built them, first question is, does one molecule have an internal plane of symmetry? So pick one up and see if you can find that internal plane of symmetry. If I sliced this molecule down this axis here, this plane, we can see the red certainly does not reflect the blue. So this would not be an internal plane of symmetry. But if I rotate it and slice it right down the blue, red, and central atom on that plane, the black reflects the black, half the blue to the other half of blue, and half the red to the other half of red. So it does have an internal plane of symmetry. We can slice it in half and reflect it. And now we have to see if the mirror images, so we'll hold them, match them up like they're mirror images, are they superimposable? Well, if I overlay it this way, does that match? No, but if I rotate it, now we can see the red overlaps with red, the blue overlaps with blue when I overlay the central atoms, and both hydrogens overlap as well. So these mirror images are superimposable. So this gets a check mark as well and tells us that this is also not chiral. So then we go ahead and we add our green ball. So we're going to build it just like we see in the picture. So I'm going to have red pointing up, green pointing towards one another. So I'm going to rotate this and add the green ball and build it so that these are mirror images of one another. The blue and the blue, red up, blue this way, and black's pointing away. Or, of course, you could rotate this way. All these different arrangements, we can see that I have built the mirror image. So now we're going to see, does one molecule have an internal plane of symmetry? So if I cut it down the central atom in green, the red is not reflected by the black. So let's try something else. I'm going to cut it down the red and central atom. The blue does not reflect the green. What if I cut it down the blue-green? Again, the red does not reflect the black. Try as hard as you like, you're not going to be able to find an internal plane of symmetry where you could slice it and have it reflect. Same with the other molecule, no internal plane of symmetry. So then line them up again and convince yourself that you have successfully made mirror images, blue, blue, green to the back, green to the back. And now we want to overlay them. So I'm going to see if I can overlay the blue and the green. That's looking successful so far. But now the reds and blacks don't overlay. So I'm going to rotate this and overlay the red and the black. I got those two overlapped correctly, superimposed. What about the greens and blues? They can't overlay. Okay, I'm going to overlay green and blue. What about green and red? If I overlay green and red, now black and blue cannot superimpose. Try as you like. These molecules, these mirror images, are not superimposable. What we have built here is a pair of chiral molecules. This molecule is chiral. This molecule is chiral. This together makes a pair of enantiomers. They're both chiral, and these are an enantiomer pair. When we have a chiral center, a chiral carbon, we put a little asterisk, a little star by that carbon to show that it is a chiral or stereo center. These two molecules that we have built, non-superimposable mirror images, we can see they have the same molecular formula. They each have one green ball, one blue, one red, one hydrogen or black prong. These non-superimposable mirror images are called enantiomers. They're built from the same atoms, so they're isomers. They're even built from the same constitutional isomer. That central carbon has a red, green, black, and blue on both molecules. So they have the same connectivity. It's from the same constitutional isomer, but they're different in three-dimensional space. They're stereoisomers. And more specifically, because they have no plane of symmetry and the mirror images are non-superimposable, we classify them as enantiomers. Now, these two molecules, whatever those colored balls represent for different functional groups, they will have the same melting point, the same boiling point, same properties, except for two very important properties. One, they can rotate plane polarized light in different directions. And we're going to talk more about that on Friday. And today, we're going to see that chiral molecules interact differently with other chiral molecules. Those are the only two unique things about these different molecules. And we know in our bodies, our proteins, our sugars, our DNA, those are chiral. So you can imagine a lot of medications that are also chiral will interact with your body differently depending if it's this enantiomer or that enantiomer, because these two molecules will interact with your proteins differently. They'll interact with your DNA differently. So it's important that we can identify these and classify them and make sure we're using the exact right molecule that we want to use. So if a molecule doesn't have an internal plane of symmetry and its mirror images are non-superimposable, those are two definitions that tell us that it is chiral. The third definition we're now adding is that if that molecule or that central carbon has 4 different substituents, so an sp3 hybridized carbon, 4 unique substituents, 4 different colors, 4 different functional groups or different atoms. If there are 4 different ones, then we can classify that carbon as chiral. And we can classify that as a chiral center or a stereocenter. We put a little star there. Because it's chiral, we know it doesn't have an internal plane of symmetry. We can't cut it in half and reflect half of it. In contrast, as we saw on the previous slide with our chart, if carbon that's sp3 hybridized only has 1 or 2 or 3 unique groups, meaning 1 or 2 of them are repeated, then it is achiral. It has an internal plane of symmetry, and we don't have to worry about whether it is a stereocenter. So moving forward with our definition of identifying stereocenters, we want to identify if a carbon atom has 4 unique groups. Now, so far we've been using colored balls, and those are usually fairly straightforward to identify. Greens and reds can be tricky to identify sometimes with different levels of color blindness. But we need to be able to look at different functional groups and see if it gives us 4 unique substituents. It's important that we look at the entire group, because sometimes these substituents, the functional groups or pieces that are attached to the central carbon, can get really big or really long. But we have to go all the way down those substituents to see if they're different. So for this central carbon here, we can definitely see that a methyl group and a chloro group are definitely different. So we definitely have 2 unique groups. But then I see CH2, 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 something, 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 and I'm not sure if those are the same or different. So I'm going to count 1, 2, 3, 4 versus 1, 2, 3, 4, 5. One of them has an extra carbon and hydrogens. Therefore, the group on the left and the group on the right are unique. They're different lengths, therefore they count as different substituents, and therefore we have a chiral center or a stereocenter. So looking for 4 unique groups is sometimes quite straightforward, and sometimes it requires a little bit of a deeper analysis. And sometimes this applies when we have a cyclohexane or a cyclic group. So let's look at this example here. We want to figure out if the carbon atoms have 4 unique substituents. So with the molecule on the left, the carbons and hydrogens haven't been written in for us, but we have good practice identifying them. To make this a little bit more straightforward, I'm going to go ahead and add in the implied hydrogens. Rather than doing all this calculation in my head, I want to be able to see all of the atoms. And you know that every bend is a carbon, but my picture is going to get really messy if I draw the carbons in. So you know they are there. Okay, so I want to look for carbons in this molecule that could be chiral, or that are chiral, if they have 4 unique groups attached. Okay, so I'm going to start with the red ball that I just drew here. That carbon has 2 hydrogens, so it's definitely not 4 unique groups. Any carbon that has 2 matching groups, like 2 hydrogens, is not going to be chiral. So what I want to decide now is if the carbon that has a little square around it, is that chiral or is that not chiral? And you'll see right away, I forgot to draw in one more hydrogen. There we go. That carbon also has an extra hydrogen. Well, I'm going to now compare these 4 different substituents and see if they are unique. So this carbon, I'm going to color it in blue. It has a hydrogen and a methyl group. Those are definitely different. But then, if I go down this direction, I hit a CH2. If I go down this direction, I hit another CH2. So I'm going to go to the right and find a CH2. And I'm going to go to the left and find a CH2. So far, they match. So I'm going to keep going. I go further down on this side, I find another CH2. I go further down on this side, I find another CH2. That matches. So I go to the next spot, CH2 and CH2. And at this point, I can see there hasn't been a difference yet. Of course, I could go infinity loops, but please don't do that. Once we get together, then we can see we haven't come across a difference. So therefore, these two substituents are actually the same. If we go to the left and we go to the right, we can't tell the difference between those two substituents. Now this might be a little strange. So I have brought my cyclohexanes here to actually build this and see if we can actually overlay these molecules if they are indeed the same. So I've built my cyclohexane. The red ball is going to be my methyl group, and this one is coming towards us out of the plane of all those carbon atoms. If I turned it into a boat and a chair, there's my methyl group coming towards me. Now I'm going to build the same thing, but now I'm going to have my methyl group going away from me. So now it's pointing down. I want to see if I swapped those two directions, are these different molecules? Is this a chiral center? We can already see it has 1, 2, at least 3 unique groups, but is it the same if we go around? So I built one with the red ball coming up, one with the red ball going down. If we try to overlay these and squish them down, you can see the red and the black don't overlap. But what if I turn this one around? Now it's going away from me, and it's going away from me. And I can see when I overlay it, everything perfectly overlays. The molecule on the left, this carbon here, is not chiral. When I swapped these two positions, I didn't make another molecule. It's exactly the same molecule because I can't tell the difference between these two side chains. So that spot is not chiral. Now we're going to do the same exercise, but with the molecule on the right. So I'm going to draw in my implied hydrogens. And I want to look again if that is now a chiral center. Well, I can see the methyl group and the hydrogen are certainly different. So that's different from that. But now I'm going to go to the right and to the left. I get a CH2 and a CH2. That matches. So now I'm going to go down. One hits a carbon that has a hydroxyl group. The other spot just hits another CH2. That's a difference. If we go to the right, we get the one with the hydroxyl group. If we go to the left, we don't have a hydroxyl group. So now I can see both of those down substituents are different. So therefore, I can count 4 unique groups off of that carbon. Therefore, we can put a star here and identify that as a chiral carbon. If I go back to my model kit over here, it's like I added a green ball or a methyl group over here. And if you go ahead and build both, one with a methyl up, one with a methyl down, we will not be able to overlay them because they are now unique. So the molecule on the right has a chiral center there, and we already drew in our hydrogens, actually has another chiral center over there as well. It has a bottom right carbon, has a hydroxyl, a hydrogen, a CH2 that way, and a CH2 that way, but the one to the right hits a methyl group. So the picture is getting messy, I agree, but we need to follow along until we find a difference to identify our chiral centers. Okay, so we now know how to use wedges and dashes to talk about three-dimensional molecules. But the next one I want to show you is called a Fisher projection. Hands up, who has used Fisher projections already? Okay, that is like next to nobody. So, important, we need to know how to interpret Fisher projections. It's another way to draw molecules in 3 dimensions. And we know that lots of molecules, whether one group is pointing this way or that way, makes a completely different molecule, a different enantiomer, as a different stereoisomer. So when we use a Fisher projection, we're using intersecting lines, a line that's vertical and a line that's horizontal, and they make an X. And we don't see any wedges or dashes, but we have to apply those ourselves. The Fisher projection on the left is the way that a lot of sugars are communicated. In biochemistry, you're going to see Fisher projections all the time. So we need to know how to interpret it. So that intersecting line, vertical and horizontal, means the 2 horizontal lines are wedges. They're coming out to give you a hug. That's how I remember it. The up and the down are going back and away. So when you see a Fisher projection, know that the sideways ones, the horizontal ones, are coming out to give you a hug, and interpret that as those wedges coming towards you. Because this helps to communicate the 3D structure of that molecule, which is essential for identifying different types of stereoisomers. This Fisher projection on the left here is a really common way to do sugars, which are our carbohydrates. And you're going to see these coming up. Here, we just had a small molecule with one stereocenter. That carbon atom here had 4 unique groups. Here, we actually have multiple stereocenters because we have multiple carbons that have unique substituents. So when we see this, draw in your book that those horizontal ones are actually wedges coming towards you, and the ups and the downs are going away from you. So I built one of these before I came to class today. So at the top of my molecule, I have my aldehyde, my CHO. And we mentioned last class, when you see that CHO, we need to know what it means. It's a carbon with a double bond to oxygen and a single bond to hydrogen. So this is our aldehyde. So when you see CHO, know that it's a carbon double bond with a hydrogen. So here is my carbon with a double bond. These are just the lone pairs of electrons. I didn't really need to put them in. And here's my hydrogen. Then I'm going to look at my first stereocenter right after the CHO, the aldehyde. On the right, coming towards me, I have a blue ball showing my hydroxyl group, my OH. On the left, coming towards me, is my hydrogen. The aldehyde is pointing away from me, and the rest of the molecule is pointing away from me. I can see the aldehyde is certainly different than a blue ball, which is different than a hydrogen, which is different than the whole rest of the molecule. So this is a chiral center. That's where we got our first star. Then we go down, keeping the rest of the molecule below us, pointing away from us, rotate to the next chiral center. Now the hydroxyl group is on the left, coming towards me. Hydrogen is on the right, coming towards me, and the rest of the molecule is going away from me. Again, another chiral stereocenter. And we rotate up to the next one. I have a chlorine coming towards me on the right, hydrogen coming towards me on the left, and then the methyl group down there, another chiral center. So this molecule here, this Fisher projection, could look like this, or we could draw it as a Fisher projection and look at each stereocenter as we go through. So we want to indicate all the chiral carbons on the following molecules. We just did this one a moment ago. So we're not going to go through this one again, but we will do the molecule on the right, our sugar, our aldehyde. This top carbon here has that aldehyde group, C double bond O and H. That's unique. The hydroxyl is unique. The hydrogen is unique. And the rest of the molecule is unique, which tells us that is a chiral center. We could do the same thing with the next carbon, a hydrogen, a hydroxyl, the top part of the molecule with the aldehyde, and the bottom part of the molecule with the alcohol. 4 unique groups, therefore that is another chiral center. And we could continue this process and see that each of these intersecting lines is a stereo center. So your turn. How many chiral centers are in this molecule? Add those implied hydrogens, work with the person beside you, and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, so we're split between 2 and 4, and the correct answer is actually 4. So let's chat about this. Okay, first one that jumps out at me is this carbon right here. It has a hydroxyl group, a hydrogen, the molecule going that way, and the molecule going the other way. When we count this out, we get a CH2 and a CH2. That matches, so we have to keep going. CH2 and a CCH. That's different. Right there, we can see the molecule is different, so those 2 substituents going different directions are unique. The next one that's unique is the one in the middle top there. It has a hydrogen, and then it goes down to a carbon with 2 carbons. That's different. The differentiating feature up at the top, it goes to CH2 and CH2. That matches. But then the next carbon has a methyl group. The next carbon over does not. So when we move over this way, we can see those substituents are different if we go to the second carbon. Next one, that bottom one for the same reason. And then the final 4th carbon that has the methyl group, the hydrogen, the short way around and the long way around. So you want to go all the way along those carbon chains until you find the first unique difference. So 4 chiral centers in this molecule. Thumbs up if that makes sense, because that was a very low fraction that chose 4. Okay, if you have questions, come see me after class. Let's keep moving. So we now know that there are chiral centers, that we need to be aware of these different chiral centers. But now we don't want to just say this one and that one, or the one I want and the other one. We need to have a communal way to talk about different stereo centers. Is it the mirror image this one or the mirror image that one? So we are going to come up, well, someone else already came up with a method to be able to distinguish these different stereo centers. First thing we're going to do is assign priorities. And you're welcome. The priority rules are the same as the ones we use for EZ. So that means we're going to look at atomic number, look at the atoms that are directly attached. Highest atomic number wins. That's it. Well, that's rule 1. Rule 2 is if they tie, keep going. And rule 3 is if you have double bonds, count that one twice. But the same rules apply. So we assign priorities. And then, very important, we place the lowest priority group pointing away from us. And then we look at priority 1, 2, and 3. And we need to see, does it move in a clockwise direction? Who actually has like an analog clock on their wrist? Like a clock that goes tick, 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 tick like this. Okay, very, very, very few. Next to very few people. Okay, so as a reminder, clockwise is the way a clock goes. You probably don't see a clock in your day-to-day lives anymore. So look, that's the way a clock goes. Those good old-fashioned analog clocks, that is called clockwise. Now, 1, 2, 3, if you turn your steering wheel clockwise, you go to the right. So clockwise is called R, because it turns your car to the right when you go in a clockwise direction. Well, the other direction, your other right hand, if you turn your steering wheel the other way, if you assign priorities and went 1, 2, 3, 4 is pointing away from you. You turned your car like this. Which way does your car turn? To the left. And long ago, people who were left-handed, it was considered sinful or sinister. I'm left-handed. Thankfully, I was allowed to continue writing left-handed. Our teachers have overcome the idea that it was sinful and sinister to be left-handed. But that's where the S comes from, the sinister or opposite way. So counterclockwise is this way. That's not the way a clock works. Anti-clockwise, counterclockwise, or S. So now we're going to build these. So follow along with me. Pull out one of your tetrahedrals and choose 3 colored balls. I think rainbows are beautiful, and it's the only color pattern that I know. And the colors that you have in your kit that match the colors of the rainbow are red. You don't have orange. You don't have yellow. You have green. You have blue. And you don't have purple. But you do have red, green, and blue. So my favorite practice is to give priority 1 red, priority 2 green, priority 3 blue. Because then I can remember colors and numbers better. If you have a different system, do whatever you want. But this is what we're going to do in class. So 1 is going to be red. So we're going to go ahead and build the molecule on the left. Red, pointing up. Red, orange, yellow, green is priority number 2, pointing to the right. Priority number 3 is green. Sorry, blue. What did I say? Red, orange, yellow, green, blue. 1, 2, 3. We're going to point 4 away from us. Hold number 4. Red, orange, yellow, green, blue. 1, 2, 3. Which way is my hand moving? Or if I turn my steering wheel this way, I'm turning to the right. This is a clockwise direction. Therefore, this is the R enantiomer. Put that one down. Build the one on the right. So red pointing up, red, orange, yellow, green pointing to the left, blue pointing to the right. 4 goes away from you. Hold number 4. Red, orange, yellow, green, blue, the colors of the rainbow. This is counterclockwise. If you turn your steering wheel this way, your car will go to the sinister direction, the left. This is counter or anti-clockwise. Therefore, this is the S enantiomer. I have the S in my left hand, the R in my right hand. Notice how they are perfect mirror images of one another. They are non-superimposable. These are enantiomers. Red, orange, yellow, green, blue. Did I just switch these? This is the S. This one's the R. Now, I need a volunteer who knows clockwise from counterclockwise. Would anyone like to come on up? Who knows clockwise? Come on up. Actually, I'm going to come to you to make this a little faster. Okay. I have number 4 pointing towards you. From my perspective, I see red, orange, yellow, green, blue. 1, 2, 3. From your perspective, is my hand moving in a clockwise or counterclockwise direction? Can you say it really loud?
Clockwise.
Okay, from your perspective, it is clockwise, and you are correct. From my perspective, it's counterclockwise. 4 is pointing towards you right now, and I set that up purposefully wrong. Towards me, it looks like counterclockwise. To you, it looks like clockwise. If I now make it correct for you, 4 is now pointing away from you. Red, orange, yellow, green, blue. 1, 2, 3. What direction is this now? Counterclockwise. Correct. If you have 4 pointing towards you, you are going to get exactly the wrong answer. So turn it around, point 4 away from you, and you'll get the correct answer. Thank you very much. So let's go ahead and assign R and S to some molecules. So we're going to assign priority rules, same rules as our E, Z. So starting with the carbon on the left. First off, I can see it has a stereocenter. It has 4 different substituents. It's connected to a carbon, a nitrogen, and a hydrogen. Assigning EZ rules, I look for highest atomic number directly attached. So I'm deciding between nitrogen, carbon, and hydrogen. Nitrogen has the highest atomic number. Carbon ties. Hydrogen has the lowest atomic number. Guess what? Hydrogen is always going to have the lowest atomic number. Hydrogen, if it's one of the substituents, is always going to be number 4. So then I have to decide between carbon and carbon. Well, the top carbon is connected to 3 hydrogens, so I could make its priority list as H, 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 as we did in EZ. And this bottom substituent, COOH, when we see that, we need to know that that's the same as C, double bond to O, and an OH. This is a carboxylic acid, or a carboxyl group. So if I write out the list, the priority list for the bottom carbon, the COOH, using my phantom rule, it's connected to oxygen and oxygen in the double bond, and then oxygen with the single bond to the hydroxyl. So then I can compare my groups, OOO to HHH. O has the higher atomic number. Therefore, the COOH has higher priority than the CH3 group. I'm deciding for places of 2 and 3. COOH is place 2. The methyl is priority number 3. So then I can go ahead and build my model. I'm going to make red priority number 1, and it's coming towards me. Red, orange, yellow, green is going to be number 2, and that is in the plane of my paper pointing down. 3 is blue, pointing straight up in my paper. So I've built it to exactly match what I see, if this is the plane of my page. I take number 4 and I hold it, and then I go red, orange, yellow, green, blue. Am I clockwise or counterclockwise here? What do we think? Is it R or S? Hands up for R. Hands up for S, and S is correct. Good stuff. In this picture, the hydrogen was already drawn away from us. So we built it because that's a good practice to do. But since 4 is already pointing away from us, I can go 1, 2, 3 and see that anti-clockwise, counterclockwise direction already. Okay, let's do the Fisher projection one now. So first off, I see two intersecting lines with no wedges or dashes, which can make it more difficult to interpret. But we know the horizontal ones are always coming out to give us a hug. So you can go ahead and draw those wedges in if that's helpful. Then we're going to go ahead and assign priorities. I have nitrogen, carbon, carbon, and hydrogen. Nitrogen has the highest atomic number, hydrogen the lowest. Then I have a methyl group. It's attached, that carbon is attached to 3 hydrogens. The carboxylic acid has a double bond to O and a single bond to O. So the OOO list wins over the one with H's. So priority 2 and priority 3. Fisher projections are much more challenging to reorient in your head to get 4 pointing away from you. Right now, I'm just going over to my model kit. I have priority 1, the amine coming towards me on the right, hydrogen coming towards me on the left. Red, orange, yellow, green is priority number 2. I'm pointing that up away from me, and 3 down away from me. Right now, the hydrogen is pointing towards me. So I'm going to take my model that I just built and turn it around so that I'm looking at this from the right direction. If I didn't do that, I'm going to get exactly the wrong answer, unless you can do really good manipulations in your head, which you're welcome to try. So red, orange, yellow, green, blue. Is this R or S? Go ahead and shout it out. R is correct. You can imagine, if you were looking at this, you'd have to imagine, if you just looked at the page without your model kit, the hydrogen is coming towards you, and so you have to like come from behind over here and look at it from like backwards perspective. You can do that, or you can build the model, match it, move it, and fully confidently assign R or S. We're going to wrap it up there today. We're coming back on Friday to finish up. Bring your model kit, and I will see you on Friday.